Okay, that's magical. Let's go to question 36. In question 36, you literally have a hailstone, which is ice falling in the sky, initially stationary at the base of the cloud. So you have a cloud, and you have a stone here, and it's stationary. Falls vertically towards Earth. Now the hailstone falls down to Earth. The diagram shows the magnitudes and directions of the forces acting on the hailstone as it starts to drop. So, at the start, this is what you have. You have the weight component, W, very large. The upthrust due to A, very small, because it's just beginning of the fall. And the viscous force, in this case, viscous force is V, it is this small. Again, what is viscous force? Viscous force is the resistance due to fluid. Okay? Resistance due to fluid will be that much. So in this question, which diagram shows the magnitude and direction of these forces when the hailstone attains a terminal constant speed? So now we're in terminal velocity, which is just a posh name for constant velocity. In the dynamics topic, we record this as an object which has its weight being balanced by, in this case, in previous topic, by air resistance, which in this case is just the viscous force, the name for the viscous force. Hence, when these two is balanced, the resultant force is equal to ma is equal to 0. Remember again, when resultant force is equal to 0, two things can be happening. An object can be stationary or it can be moving with constant velocity. In this case, terminal velocity, you're just moving down with constant velocity. Not increasing the speed, but just maintaining the speed. Now in this question, we have an additional component, upthrust. How does upthrust enter this picture? This is assuming there's only air resistance. But what if A also provides a force pushing it upwards? And then we have the different diagrams, which diagram shows the magnitude and direction of these forces when the hailstone attains terminal constant velocity in the A of uniform density. So all you need here is to find a diagram where your weight, your upthrust, and your viscous force all by scale balance out each other. We know in this case air resistance and this upthrust due to A. You have to know that the upthrust due to A will be much, much smaller than air resistance or the viscous force. This is one key information you need to know. Because if the upthrust was actually higher, just like water, if you go to water, you walk through it quite easy. But if you try to walk through water, you discover that water resistance is much, much more higher, and if you are literally floating, the upthrust is also much more higher. But we are planning A, so just remember air resistance is much greater than upthrust. Once you notice that already, you already have the answer to the question, because the only answer that has an upthrust that is smaller than the viscous force is D. So you're looking at weight, W, upthrust, U, and then you have your volume, your viscous force, sorry, not volume, your air resistance. Yeah. Both of these should balance each other in order for you to go back to your dynamics component. Okay. So again, the key here, remember, air resistance is much more higher, the upthrust, that is the air pushing you upwards, is minor compared to water. That's why in water, you can float, by air, you don't really float. Okay. So I hope this helps you. So I hope you understand this video.